welcome to the week 6 of the course Biological Data Analysis and Visualization with R. In this week we will be talking about regression models and how to apply regression models on biological data and the kind of insights that you can generate using regression models. So, we will first start with linear regression. So, this is something we will be talking about. We will talk very briefly about the concept of linear regression. We will talk about very briefly again ordinary least squares method. So, it is actually important to know how these methods work and what are the assumptions when we apply these models. So, that is the first part. So, we will learn about this and then subsequently we will apply linear regression on biological data and we will build something called predictive models. Okay. So, we have most of you have learned about a bit about this y equals to mx plus c kind of equation and estimating m and c, and maybe you have also learned about ordinary least squares method, but we will talk about more towards application of these models in biological data and how we can build predictive models. So, that is the agenda for this week. So, in this class we will be talking about introduction to linear regression first, and then we will be talking about ordinary least squares method. So, let us start with linear regression. So, what is linear regression? It is modeling of a linear relationship between a dependent variable and one or more independent variables. So, the dependent variable is sometimes also called the response variable, and we also have the one or more independent variables, or we sometimes call them as features, right. So, the idea is to predict the response from the features, right. So, connect response to the feature variables. Okay. So, this usually takes this form y equals to wx plus b, very similar to what we have learned before probably in school, y equals to mx plus c, right. That is the same form. I have written them just the coefficient as w, that is the weight, or b, and the c instead of c I have written b, which we call as bias or error. Okay. So, here in this equation y is the dependent variable or the response variable, and we have one independent variable which is the x, right. So, this is the most simple form of linear regression, and we call this simple linear regression. Okay. So, this is something all of us have learned in school. Now, this could be useful but in biological data, but often we have multiple independent variables, right. So, when we work with big data sets in biology, there will be multiple independent variables and sometimes multiple dependent variables as well. Okay. So, we will talk about this variation of simple linear regression. So, we will go into more complex situations. So, the first scenario where we have multiple independent variables, the situation would be like this, right. So, we have the dependent variable or the response variable y, which is modeled as w1 x1 plus w2 x2 plus w3 x3 plus b, right. So, we have three independent variables here, x1, x2, x3, and for each of them we have these weights w1, w2, w3 corresponding weights or coefficients, and we also have the b or the bias term. Okay. So, this is more general form, and this is something that is more applicable towards biological data, where we have multiple independent variables from which we want to predict a response variable, right. So, y, and this is called multiple linear regression. We also have another variant of this, right, which I mentioned, where you have multiple dependent variables or multiple response variables, right. So, we will take examples, right. When you go into hands on, we will take examples and we will see, right, when you can have multiple independent variables, what kind of variables those could be, or multiple dependent variables, what those could be, etc. Okay. So, this when you have multiple dependent or response variables, this is called multivariate linear regression. Okay. So, again in the hands on, we will very briefly see how we can apply multivariate linear regression to biological data. So, as I said, right, instead of one y, now we have three y's, right, y1, y2, y3, and each of them depend on these independent variables x1, x2, x3. Okay. So, we have y1 equals to w11 x1 plus w21 x2 plus w31 x3 plus b1, right. So, these bias terms are different as well as the weights are different. So, the dependent variables y1, y2, y3 they depend on x1, x2, x3, but the weights are different. And as I mentioned, right, y1, y2, y3 are independent variables, x1, x2, x3 are sorry, y1, y2, y3 are dependent variables, not independent variables, and x1, x2, x3 are independent variables. Wij, these are weights or coefficients, and bi are bias. Bi terms are bias or error terms. Now, so the question that we have once is how do you actually estimate these weights, right? So, these weights will vary, right, depending on the biological system, and how do we estimate these weights and the bias term, okay? And the method that we have learned before, perhaps some of you have learned in school, is ordinary least squares or OLS. Okay. So, here it is, write the equation y equals to wx plus b, and we want to estimate these weights w and b. Okay. So, how do we estimate these w and b? So, we have x values and we have y values, corresponding y values for x values. From that, we would like to estimate w and b. So, here it is, right. So, I have fitted this line, right. So, the idea is we start fitting lines y versus x, and what we want to minimize is something called the residual. Okay. So, this is the idea is to find the best fit line, right, best value, the values of w and b that best fit the data. How do you find this best fit is by looking at this residual. So, what is this residual? Epsilon I is yi minus yi hat. This is the predicted value. So, yi is observed value, right. So, let us say we have 10, so I equals to 1 to 10 x values and 10 y values. So, we plot these x y, right. We have these corresponding pairs, x y pairs, and for each of them we try to fit, right, this w and b, so that we minimize this residual. Okay. So, the residual is difference between observed value and the predicted value. Predicted value is the yi hat, which is wxi plus b. Okay. So, we fit this w and b in such a way that we minimize the sum of the squares of the residuals. Okay. So, sum of the squares, because some of these residuals would be positive or and some of the residuals would be negative. The goal is to minimize the total sum of the squares of the residuals. Okay. So, the residual, as you can see, is shown by this dotted line in these plots, right, and we want to fit a line by varying w and b. We want to find the values of w and b in such a way that we minimize this sum of squares of this distance of these points to the line. Okay. So, that is what ordinary least square does. Okay. So, without going into further detail how this works, at least we have some idea. Let us talk about the assumptions that we make when we are fitting a linear model, right. So, when you are fitting a linear model, so what we are assuming is that there is a linear relationship between dependent and independent variables. Okay. This is something that is probably obvious, right. Otherwise, we will not be able to write that equation y equals to w1 x1 plus w2 x2 plus b, right. That kind of equation we will not be able to write unless we assume there is a linear relationship. There are other assumptions as well. This is something we should be aware of. We may not be able to satisfy all these assumptions at all times, but we should be aware of this, because if these assumptions are violated, they might change the robustness of the model, right. So, the model will not be that robust if some of these assumptions are violated. So, the second assumption is that there is equal variance of the dependent variable at all values of the dependent variable, right. So, if you take different y values, right, and you might want to measure, right, the variance at each range of y values, right. So, the assumption is that the variance of data points within each range is more or less equal. Okay. So, this is something that is present, but this, as we know, this may not always be true. Okay. So, this is something again we need to be aware of. This is an assumption. The third assumption we have is there is no perfect multicollinearity. So, this is something we will be discussing in much more detail. What is multicollinearity, and how we can address multicollinearity. So, what is multicollinearity? So, multicollinearity refers to a situation where the independent variables are highly correlated with each other. Okay. So, this is something that we will often see in biological data sets as well. Okay. So, there are many features, many independent variables that will show very strong correlation within themselves. Now, if we have perfect multicollinearity, then that means there is perfect correlation, right. That is probably very rare. The problem will be if you have multicollinearity, very strong linear correlation between independent variables, that will affect the outcome of the model, right. So, when you go into predictive model, we will have problem with this predictive modeling, we will have problem with estimating the coefficients of this for each independent variable. So, this is something that we need to keep in mind. There are ways to address these issues, and this is something we will be talking about in one or two classes later on. Okay, so this is another assumption. The other assumption that we have is the mean of the residuals is 0. So, what it means is that probably the points are equally distributed across these lines, right. So, that is something that will lead to mean of the residuals to be 0. Okay, so there are also a few other assumptions. Again, we will not be going into a lot of details of this, but these are the major assumptions that is that we should be aware of, because if we violate some of these assumptions, we might have less robust models. Now, moving on to the another term that is something that we use is called generalized linear models, right. So, when we are talking about linear modeling, so when we have, let us say, data over a large range of values where we have skewed distributions, or if we have categorical or ordinal dependent variables, right. So, instead of continuous values, we have categorical variables, right. So, we have different classes, and that is something that you want to model as a linear function of independent variables. Okay. So, in those cases, right, all these situations, they come under something called generalized linear models. Okay, so what are the applications of these linear models? So, one of the things we can of course answer is how much of the variation in the dependent variable is explained by the independent variables, right. So, this is something that we can answer, right, how well these independent variables can explain the variation in the dependent variable of the response variable. This is we can answer here. And the second is of course which of these independent variables has the strongest linear relation with the dependent variable. That is something we can also understand here, right. So, which of these independent variables will affect or impact or influence the outcome, right, the most. And finally, we can use these models for predictive modeling, and this is something that is very, very useful in many cases. So, when I say predictive modeling is we want to predict the outcome based on the model that we have built. Okay. So, let us say we have built a simple linear regression model where we have y and x, one dependent variable, one independent variable. We have estimated w and b. So, we now know the relationship. Based on this, if we now get new data points x, right, we want to predict what would be the value of y. Okay, so, this is what we call predictive modeling. So, once we have built a model based on certain data points, we can get new values of x and predict what would be the value of y. Now, how does this help actually? So, this is something we can use for predicting certain features, right, certain outcomes. But what is also very interesting is that we can use predictive modeling to identify the features or independent variables that actually can predict the outcome in the most, right. So, which influence the prediction. Okay, so, these are variables or features in biology that could be very interesting to study. Okay, so, this can give us new insights. Okay, so, with that background of linear models, linear regression, ordinary least squares, the assumptions, now I will just very briefly mention what we will be covering in this class as well as subsequent classes. So, here in the hands on we will be talking about simple and multiple linear regression. So, that will be in this class. Following that we will be talking about predictive modeling with linear regression, how to build predictive models, using linear regression, and how do you actually start predicting, how do you see the quality of predictions and which variables are the best predictors, those kind of analysis we can do. We will also address the problem of multicollinearity, and how do we address the problem of multicollinearity. There are different ways of doing this. Again, we will be talking about that, and we will actually do the hands on to address the problem of multicollinearity. And finally, we will be also doing something called stepwise regression. Again, so let us say we have like 10 variables, out of which maybe 5 has very strong relationship with the dependent variable or response variable. Now, what stepwise regression does, it actually identifies combination of variables that actually gives us the best prediction. Okay, so this is something that is also very useful, right, for identifying the combination of these features or combination of independent variables that could help us identify or predict the response. Okay, so with that background, let us now dive into the hands on. So, we will start with very simple linear regression and multiple linear regression, and we will look into the data and then build those simple linear models. So, let us now move to R. So, here we have the R console. Let us see where we are in terms of directory. Okay, so, we are in the linear regression directory, right, class 26 to 30, and we will start with the data set called the filtered merge data is. So, this is something, this data set we have already seen before. Now, we will use this data set in such a way, right, we can build very interesting linear models. Okay, so let us start, right. So, how do you first start with this is like, let us load the data. Okay, so, that is what I am going to do. And okay, so here is the data, and let us look at the names of these columns, right. So, we know how this data looks like. If you have seen, if you remember our earlier classes, so what we have in the columns are certain values, right, certain experimental measurements that we have compiled together. So, again, without going into all the details of how these measurements have been done and what they actually mean, right, that will take a lot of time to discuss how we actually arrive at these measures. Let us just focus on these measures, like, so we have a lot of measures that we have collected for this organism, and we have the gene list, right. So, for each gene we have these measures. So, average expression in two different conditions, we have DMYPD or DMYPD class. So, DMYPD, DMST, these are noise values, expression heterogeneity values. Then we have whether this gene has data box in the promoter or SCRG element in the promoter, the promoter nucleosome occupancy, that information here. Then down there we have also the transcription factor binding information, etc., etc. Okay, so there is a lot of information, but what is also you should notice is that we also have a lot of NA values, right, where information is not available for some of the genes. Okay, so if you do not have this information available, we have to use the term NA. Okay, so again, this is very realistic, right. In many cases, when you work with biological data or any other data, you will see many independent variables we will not have any measurement. So, we will have to deal with NA values. Okay, so we will see how we actually deal with these NA values later on. Okay, so when we have to do multicollinearity analysis. Okay. So, here is the data, right, and we can also see the names of the columns. Okay. Again, just a list of the names of the columns that we have just also seen, right, first few columns at least we have seen now. Okay, so, what we will do is we have loaded the data. There are some pre-processing that we are going to do. Okay. For that, we will need these libraries, right. So, library PLS is partial least squares, which will require. So, what we will do is we will load this library, and then we have the library DPLYR and TiDR, which we have talked about. These are libraries that we require for reorganizing or transform the data, right. So, this is we have talked about in earlier classes already, and all right. So, we have attached all these packages now, and we can use them to reorganize our data. Now, let us look into the first few pre-processing steps. Okay. Here it is, right. So, if for example, right, the first step is this. So, I will explain the code what happens. So, tab is tab, right, this data set we have loaded, right. What we are doing is we are taking only those columns where, so column sums, col sums is the column sums is NA tab, right. So, taking this tab data is NA, right, how many NA values are there, and column sums should be less than 100, okay, and we will be taking only those columns for our analysis. Okay. So, if you have a lot of these NA values, then these columns or independent variables are not very interesting to us, right. So, that is why we need to filter out certain columns that where you have a lot of NA values. Okay. So, for that first let us look into the dimension of this. So, we have 2160, right, 2160 rows and you have 288 columns, right. But when you say 800, right, so what it means for 800 genes we have NA values, right. So, it is close to 40% or so we have NA values. So, those features or independent variables are not very interesting for us. You can make this more stringent, right, you can say 500, 200 and so on, or you can make it more relaxed, right, say 1000, 1200, but for now let us, so the results will change if you change those thresholds, but for now let us keep it at 800, okay. That is something we feel is a good number. Okay, so the next thing what we are going to do is we are going to choose certain columns, right, for our analysis, and what we are going to do, let us say, is, as I said, right, let us so after this filtering let us look at this. Okay. So, it seems all of, so some of these columns, right, is about, so most of these are 266 columns, they are fine, but out of which maybe like 22, right, out of 288, 22 or so they have a lot of NA values and those are not useful for us. Okay. Now, let us now look into the column names of this new data again, right. So, here we have the new names now, and what we are going to do next step is we are going to choose the dependent variable and the independent variables. Okay. And let us say as the dependent variable, let us say we want to predict this DMYPT, this is the noise value that we want to predict based on other features that we have. Okay. So, the other features start from here, right, STRE element. So, these are the independent variables that we are going to choose. Okay. And as you remember, right, we use this dplyr package and we can select, right, certain data set, and this is what we are doing here, tab field 1, right, filter data. We are taking tab and select 4, right, the column number 4, which is the dependent variable, and then from the elements from STRE and metal, right. So, as you can see from, if you look at the name again, right. So, we choose from here STRE and to the last element, these are the independent variables in our data. Okay. So, that is what we are doing. You can do it in different way as well, which I have shown here. You can show this 472 266. You can also give the column numbers as well, right. You do not have to always write this, but this is probably simpler for us rather than counting column numbers, etc., keeping track of the column numbers. Okay. All right. So, this is what we have now, and as you can see, we can just have a look at this. So, you will see, right, we have selected all of them except, right, the first few ones. So, this is the first one, DMYPT is our dependent variable or the response variable which we would like to predict, and rest of them are independent variables. Okay. We can do a few more filtering steps here, right, and I will again explain what this means. Is filtering 2, second step is take this filtered data, filtered 1 data, and then apply, right, where the variance, right, is not equal to 0, right, when variance of this. So, if variance in any column is 0, right, that feature is not going to be useful, right. What does this mean? Because this feature has constant value throughout. Okay. So, that feature is not going to help in any prediction because it does not even vary in the data. Okay. So, this is something we can again filter out, and let us see what happens. Okay. So, there is actually no filtering apart from tap filtering 1, right. So, there is no feature which has 0 variance. Okay. This is something we do not have in our data. So, that is good, we keep on all the features. All right. So, we can do few more filterings as you can see here. Okay. So, here we have input data filtering 2, we are selecting certain columns. Okay. So, again you might ask that why we are doing this. So, just for this example we can choose certain columns, and this is how we are choosing certain columns, right. From this filtered 2 data we have 1, then 3, column 3 to 151, then from 161 to 212, from 217 to 260. Okay. So, you might ask like why we are choosing this. This just as an example you can choose, or you can run with the full filtered 2 data. Okay. There is no issue at all with that. Okay. Now, there are few more filtering steps here you can see below, right. Here you can see some of these steps here. For example, right now we have defined the input data. From that we can define something called LM data and take only those columns, right, where column sums is not equal to 0, right. So, if again if you have certain columns where your column sum is 0, right, again everything is 0 value without after omitting the NA, right, then we do not want to use those columns, right. Again this is something because the values are almost constant, right, and then we have also we can apply this filter, the second filter, which is column sums is NLM data is less than 0.9 of the number of rows in the data. Okay, again we are filtering, right, the columns for which we have a lot of NA values or we have 0 values. So, all those things, right, in different ways you can actually do this, and similarly you can also do something called row sums, right, where LM data is an LM data, right. So, row sums means for some genes perhaps there are a lot of NA values. Okay. In that case we want to get rid of those genes, right, there is no point in including those genes in our model. Okay. So, that is something we are doing in this last part, okay, in this last filtering. Okay. So, what I will do is I will encourage you to actually run these which commands first and see what actually happens, right. So, I can show you this, right. For example, on this we can, okay. So, it will tell you, right, what is the what are the columns where the sum is not equal to 0. So, I believe it is in our data there is no column where we have only 0 values. So, this is something you should get all the columns. You can also run this where and see, right. So, is NA, how many NA values are there, sum, take the sum, that sum should be less than 90% of the number of rows. Okay. Okay. So, again the LM data is not there, so probably it is not running it. So, let us run this first, generate the LM data and then look at this. So, all these filters are applied, right, so that we get more clean data. Okay. So, we will apply these filters and see what happens at the end, right, and finally get the LM data. Okay. What I will encourage you to do is take these features carefully and look into what actually each of these commands are doing. Okay. So, here it is looking at how many 0 values are there, that should be less than 90%. Here is looking at number of rows that have NA values and how many we have here. So, as you can see, like we are now left with this table, we can also look into the dimension of this, okay, and the number of genes are actually same, remaining the same. So, it means we do not have many genes where we have a lot of NA values. Okay. So, we do not have those genes in our data. We have now 104 columns, one of them is the response variable, and we have 103 independent variables. Okay. So, we have, this is something we do like whenever we are working with the data set, just to clean up the data, right. So, we can build a good model. Okay. So, once we have done some filtering and cleaned up the data, let us now go into simple linear regression, right. I will just show you how this simple linear regression works, and it works with this command, as you can see, the LM command in R. Okay. So, we will build this simple model LM command DMYPD, and this is the sign It is saying this is y, DMYPD, this is the y and this is the x, okay, and data is LM data. So, take the LM data and consider this column as the dependent variable and non-promoter nucleosome occupancy as the independent variable, and then build the linear model. Okay. So, this is what this notation means. Okay. We have built a simple model. Here is the intercept, right, that is the bias term, and then we have the number of promoter nucleosome occupancy. This is the weight or the coefficient 0.01166. Okay. So, this is the model and we have estimated this. We can also look at the summary of this simple model, and you can see, right, the outcome, the dependent variable is significantly, right, there is significant correlation, and this is given by this t value, that is the statistic, and the p value here, which is significant. Okay. And then this is something we also use, like later on, that there will be in ANOVA we can do, etc. So, this is our results, and we have estimated the intercept or the bias term and the weight term or the coefficient term. Now, let us make this a bit more complex and let us do a multiple linear regression model. When we build this multiple linear regression model, we can use the full data, right. We can say this is the dependent variable, build the full model with all independent variables that we have. Okay. And let us run this. The notation is very simple here. We do not have to type all the name of all the independent variables. We can simply say the y is depends on dot, right. Dot means it is like consider all independent features, right. So, all rest of the features in the data. So, this is something that will run this model, and again for each of these we have this intercept plus the coefficient or the weight value. We can also run summary okay, and here we will get the importance of each of these features, right, which features show significant linear relationship with the response variable. As you can see, for example, data box is there, and you can see these stars, right. So, these stars there have some significance, these are given, right, significance codes, right. So, if p value is less than 0.001, we have 3 stars. If it is you have a dot if it is less than 0.1, if it is just a single star it is less than 0.05, 2 stars less than 0.01, and so on. Okay. So, these are the significant codes we have, and based on this you can see, right, which values, which variables, which independent variables have significant linear relationship with the dependent variable. There is another thing we should also note now is this something called multiple R squared and adjusted R squared. Okay. So, what this R square means is how much variation in the data is explained by this model. Okay. If we consider all of these independent variables, how much variation in the response variable or the dependent variable can this model explain. Okay. So, this multiple R square is 0.3 and this is adjusted R square 0.27. So, this is something we always look at, the adjusted R square. This is adjusted for number of features or number of independent variables we have. So, one of the things you can think of, right, if you increase number of features, we can always increase this R square. So, that is why we always report the adjusted R square, because this corrects for number of features that you have. At the end we always prefer simple models, right, the models where only a few features can explain a lot of the variation in the data. So, that is why we penalize or this model penalizes, right, if you have a lot of features, and calculate this adjusted R square 0.27. We can also compare this with the summary of the simple model. Okay. And here you see that adjusted R square or the R square, multiple R square is very low, right, 0.008, 0.07. So, by including these features we now explain about 27% of the variation in the data. Can we increase this, okay, and can we see whether there is multicollinearity in the data? So, that is something we will be discussing in the subsequent classes. There is another hands on that we wanted to do is the multivariate linear regression. So, here again we can now use two dependent variables instead of just one, okay. And for that we are including these 4 and 6, okay. 4 and 6, these are the noise values in two different conditions, right, and these are the first two columns, right, DMYPD and DMST, right. These are the first two columns, these are the two dependent variables that you can use, okay. And we can then apply these filters, etc. We can use this and we can build the model, right, two different models here, okay. And these models we can build using these independent features. We cannot or if we want to use DMST as feature, we can use that in this model, okay. So, we have to build this model separately for each feature, right, model 1, model 2, and then we can look into the summary of the models. There are other ways also to do this, which I will not discuss, is using the RRR library, where we can also do this multivariate modeling. Okay, so with that we have covered the hands-on part. So, let us now go back to the presentation and let us summarize what we have learned in this class. So, we have talked about linear regression, how these models are built. We have talked about ordinary least squares. So, we have some idea of this modeling approach, and we use these models to estimate the strength of linear relationship between dependent variable and independent variables, and we can also apply this to predictive modeling, which we will see in the next class how we can apply this model. Thank you.